Our topic is motion in two dimensions. When we use the term two dimensions, we are referring that if there is a point in two dimension, it must have two coordinates. One of them is x, other is y. X is along x-axis and y is along y-axis. In two-dimensional motion, the motion takes place in a plane. If the plane in which motion takes place is taken as xy plane, the coordinates of point in this plane will be represented by xy and the position vector is indicated by xi plus yj, where r is the position, vector position, and I and j are the unit vectors along x-axis and y-axis. As it is indicated in the figure, xy plane, r is the position of vector. So position vector is r indicated by line OP. XY are the coordinates of P. If we draw the perpendiculars on x-axis and y-axis, that will represent the length and breadth of the point in the plane. Now, third point is that if x1, y1 are the coordinates of the position of a particle at time t1 and x2, y2 are the coordinates of the particle at time t2, then the position vector r1 can be given by composition x1i plus y1j, and the position vector r2 will be given as x2y plus y2j. The displacement of the particle will be taken as delta r, and that will be r2 minus r1. Then we compute the values for r2 and r1, and we take x2 minus x1 into I, where I is the unit vector along x-axis, plus y2 minus y1 into j, where j is the unit vector along y-axis. So it is clear from the figure, that is again OX and OY. This is making a XY plane, and OQ line is indicating the position of the particle with coordinates x to y2, and P is a point whose coordinates are x1, y1, and delta R represents the displacement of the particle, that is from P to Q. Now, magnitude of displacement, if we wanted to find, we remove I and j and we take only coefficients of I and j and we take the square of the number, then we take the modulus and it is taken as under root. So delta R is equal to, modulus of delta R is equal to x2 minus x1 whole square plus y2 minus y1 whole square, and this whole number we take the square root. So we have written the power 1 by 2. Now the next point is that at time t, the position is given by r is equal to xi plus yj. Again, I am saying that I and j are the unit vectors along x-axis and y-axis, and x and y are the components of the vectors. The instantaneous velocity of the particle at this position will be given as v vector, that is dr over dt, where we have taken the derivative of displacement with respect to time. So we compute the value dx over dt with unit vector, that is I caps dy over dt j caps, and the number can be written as vxi plus vyj. Now speed or magnitude of the velocity will be taken as v is equal to, and we take the coefficients of I and j and we square the number and then we do square root. So we have taken vx square plus vy square, and the power will be half, or it is under root. Another important point is that if the particle is displaced from position r1 at time t1 to position r2 at time t2, then average velocity during the interval t2 minus t1 is, the average is r2 minus r1 over t2 minus t1. So average velocity will be the total rate of displacement. Now next is motion with uniform velocity. Uniform velocity means that up to the time the particle is moving, its velocity will not change. It will cover equal distances in equal intervals of time. Suppose the coordinates of the particles at t is equal to 0 are x0 and y0, and after time t, the coordinates become xy. Then for the uniform velocity, we will find that v is equal to the position, difference of the position of two vectors, divided by the difference of two times. So it is r minus r naught over t minus 0, that is equal to r minus r naught divided by t, or r will be equal to r naught plus vt. The equation is quite similar to v is equal to u plus at. Now we will write a vector form, that is xi plus yj, that is x naught I plus yj plus vxi plus vyj equal to x naught plus vxt I caps plus v naught y naught plus vyt into j caps. So our equations will become x is equal to x naught vxt and y is equal to y naught plus vyt, where vx and vy are the velocities along x-axis and y-axis. Now motion with a constant acceleration. Up to the time the body is moving, its acceleration will not change. When we say acceleration is not changing, it means the rate of change of velocity will not change. Throughout the motion, the rate of change of velocity will remain constant. So, if constant acceleration, if A is constant acceleration, then vector A is dv over dt, that is derivative of velocity with respect to time, or it can be written as d square r over dt square. This is spoken as double derivative of displacement. First of all, we take one derivative, that is the displacement derivative, that is the derivative of displacement. Whatever number we get, that is called velocity. We again take the derivative of that number. So we take 2 times derivative of displacement, and that's why its name is d square r over dt square. If the velocity is v1 at time t1 and it becomes v2 at time t2. So t1 and t2 are the instants of time and v1 and v2 are the velocities at those instants. Then dv over dt is acceleration. So we can modify this equation and we can write dv is equal to a dt. Now what we have done, we have integrated the function, that is integration of dv from limits v1 to v2. When we say integration of dv means integration of 1 with respect to v. So integration of 1 with respect to v will be v only, and that is equal to acceleration a integration dt, limits are from t1 to t2. So integration of 1 dt will be t and the limits will be from t1 to t2. Therefore, we have written the equation v2 minus v1 is equal to a into t2 minus t1. This result we got by integrating the functions dv and dt under the minimum and maximum limits. So acceleration from this function will be v2 minus v1 divided by t2 minus t1. Now the another part is, let the velocity at time t0 be u and the velocity at time t be v. So two times are indicated here. One is time 0, other is time t. Obviously t is greater than 0. So acceleration is v minus u over t minus 0. T minus 0 means t. So v minus u over t, and that v minus u over t is the rate of change of velocity, and that is what acceleration. And from this we got an equation v is equal to u plus at. The components of v will be vx is equal to ux plus axt and vy is equal to uy plus ayt. Vx means the component of velocity along x-axis, ux means initial velocity component along x-axis, ax means the component of acceleration along x-axis. Similarly, we can interpret vy. So vy is equal to uy plus ayt. Now, in the C part, what we are finding, that we are just representing velocity, and velocity is the rate of displacement. So we have written d over dt means rate of. R stands for displacement. So when we take the derivative of displacement, that will be velocity. So v is equal to dr by dt means rate of displacement, and that is equal to u plus at. Now from this number, we calculate the value of dr. Dr will be v dt, and this number becomes u plus at into dt. Now we integrate this function dr from the limits r0 to r, and initial position is r is equal to r0 at t is equal to 0. When we say t is equal to 0, the body is not moving, it is at rest. So, position vector r at time t will be, that is, integrate the function from r0 to r, dr. Integrating dr, and dr is equal to how much? U plus at into dt. So, integration of dr from limit r0 to r can be written as integration 0 to t u plus at into dt. Now we have integrated the function, and after integration we get r minus r naught is equal to ut plus half at square, or r naught means the position at t is equal to 0. So r is equal to r naught ut plus half at square. In terms of the Cartesian components, x will be equal to x naught plus uxt plus half axt square. Wherever we write ux, it is the component along x-axis. Ax means component of acceleration along x-axis. The same interpretation we give to the second equation, that is y is equal to y naught plus uy into t plus 1 over 2 ay into t square.